Hello all, welcome back. In this video we'll see one of the implementation of CAN, which is also known as Kolmogorov's-Arnold Representation Network, and it is considered as an alternative to MLP, so multi-layered perceptron. So it's like a coming topic for the large language models that we are working on, because implementation of CAN with LLM is driving new kind of models to come up. So we'll touch with how it works. We'll see a representation of the CAN network itself. I'm not going into deep what exactly or how are the mathematical things are done, because in YouTube there are a lot of videos you can share. I will also try to share the links of it. So what is the objective? We'll be implementing CAN, that is Kolmogorov's-Arnold Representation Network, using Streamlit, and also show the entire training process using Streamlit itself. Okay. So what is CAN? CAN stands for Kolmogorov-Arnold Network, or sometimes Kolmogorov-Arnold Representation Theorem. It's a type of neural network architecture inspired by Kolmogorov's-Arnold Representation Theorem, a mathematical result that states that any continuous multivariate can be represented as a superposition of univariate functions. So in that case, what happens is, like, if you have seen functions like y equal to f x1 x2 x3 x3 xn, what it does is that it passes the input features through univariate functions. Then it is broken down into like phi of x1, phi of phi 2, or phi 2 of x3, and continues till phi n of xn. Then we sum this up. So when this univariate functions are being created, we do the exact summation of this. So how do we do it? We add it as phi 1 x1 plus phi 2 x2 plus dash 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 till it reaches all of the required functions that has been created. So it is summation of q equal to 1 to n phi q to xq. Okay. Now after that, from this now when the sum is being created, we pass it through another function that results in a function of the entire summation that we have done, and finally we repeat the iteration m times. So this is how actually the CAN works, and there are a lot of videos, so I'm not getting into the deep of it. I'm only trying to represent it. So again, in simpler terms, a CAN aims to approximate complex functions by breaking them down into simpler components. It achieves this through layers of neuron. CANs typically have multiple layers of neurons, similar to other neural networks. Spline activation. Instead of common activation functions like ReLU or sigmoid, CANs often use spline functions. These functions are piecewise defined and can be tuned to provide flexible non-linear transformations. So we are not using the other activation function, we are using spline activation, and what exactly it does is that these functions are piecewise defined so that it can be tuned to provide the flexible non-linear transformation and universal approximation. The combination of layers and spline activations allow CANs to theoretically approximate any continuous function given enough neurons and the right spline configuration. So key advantages of CANs: expressiveness, they can represent a wide variety of complex functions. Interpretability, the spline functions with a CAN can be analyzed to understand how the network is transforming its input, offering some degree of interpretability. Smoothness, spline activations are naturally smooth, which can be beneficial for certain tasks where smooth transformations are desired. Now looking at the code itself. So first of all, we are looking at the imports. So if we focus on the part of the import functions itself, we will go to Visual Studio Code. Here you'll see at the top I've imported all the required libraries that are there for our usage. Make sure that the portability TFF function, that is this import that you have seen over here, it is in the current version of it is on its own itself. Now KRS also you have to install as a what you can say nightly edition of KRS that is required to directly include all of the things. So first of all, as you go back here, you see that we are implementing the NumPy TensorFlow as TF provides common neural networks dense. This Keras layers allows us to add the layers of neural network. Now TensorFlow Keras high API for building training models, and TensorFlow probability as TFP extends TensorFlow with probabilistic model tools. Streamlit is used to create the UI. Matplotlib is used for visualization. Okay. Now spline activation function. This is a custom layer that implements spline activation function. INIT initializes the layer with a specified number of knots points where the spline segments join. So we are considering spline activation function. What happens is that these points are knots where the spline segments are joining. Build creates the trainable weights for knots and the corresponding coefficient, and we make a call, take the input data and applies the spline activation function using the tfp.mat.interoperability regular 1D grid. So here again we go back to the code itself. You see this is the spline activation function that's being created. First of all, we are declaring a class for spline activation functions that uses or creates the layer. We are initializing it with knots. Typically it's 10 knots, and again we are using a super for spline activation. We are creating a build, coefficients are there, we are considering the inputs of it and returning the entire spline to the main method itself. Now we are defining a simple CAN model. So what exactly the CAN model does is so we are creating a model function, builds a simple CAN model itself, creates an input layer, adds multiple dense layers with spline activation function in between, adds a final dense layer with a single unit of the output, construct and returns a Keras model object itself. Now after that we are creating a generate synthetic data function which generates synthetic data for training and demonstration, creates x values uniformly distributed between 0 and 1, calculates y values as sine waves with some added noise. So that is how we are generating the synthetic data, and the function is being declared accordingly. Then we are training the CAN model function, compiles the model with the Adam optimizer and mean squared value error loss, trains the model on input data for a specified number of epochs, includes early stopping to prevent overfitting. So these are the things that has been applied. So here is the data generation part where we are creating the synthetic data that's being already shown on some samples. Then we are doing a model training of the CAN model with epochs as being mentioned using the optimizer Adam, and we are applying early stopping, and finally on the Streamlit tab we are calling all the functions so that we can run through the samples. We are creating the sliders on the left hand side so that it can go through the entire structure. There is a train CAN model that is being given so that we can train the CAN model itself, and again we are doing a model prediction visualization. Okay, so let's take a look at the code, how it runs. So as it is a Streamlit code, so it runs through using the command streamlit run can1.py. that's the name of the file that's been given. We'll see how it performs. It will take some time to come up. Okay, so this is the generate synthetic data. Now we can also change the number of layers accordingly. As it changes, you see the changes happening accordingly. You can also change the number of knots in a spline. then number of epochs you can also increase, but I am keeping it as it is. Now if I click on train CAN model, it is doing the training. As you can see from all the information over here. So finally it shows the training loss over epoch results that's being shown, and finally the model prediction. Okay, so that is the way we have created a CAN implementation. I think the entire concept is very new and is very useful for all of you. Continue supporting me so that I can create more implementation of CAN and other possible things that are happening, and thank you for watching.